Alright, so we'll be going over 3.4, which is about exponential growth and decay, particularly in regards to the form e to the power of x, but theoretically any function a to the power of x can be made into e to the power of x using natural log and using properties of log. So for example, 2 to the power of x is just another form of e to the power of x. You can do so by uh, well, there's like multiple ways to do it. I mean, I could probably just find what 2 is in terms of e. So ln 2, which is, I don't have a calculator with me, um, but ln 2 should be, I think, 0.693. Let me check. Um, ln 2. Um, oh, it's right here. Okay, ln 2. Yeah, 0.693. I learned that when doing chemical kinetics. Because one of the integrated rate laws involves log 2 and or ln 2 per se, and it's, I believe it's k over 0.693, so that's how I knew that, if you were curious. So that all that means is that that's Euler's to the 0.693 um, k, which is the same thing as e to the 0.693 k. So yeah, any form of this function um, you can always turn any function or any exponential function into the form e to the power of x, or k in this case I used. Um, so that can make it a little easier to differentiate for you guys, if you guys just know the chain rule. So yeah, it's pretty interesting there. So this chapter is a little bit confused, or this lesson's a little bit confusing. I mean, it was for me because I couldn't understand the practical application, and that's where I kind of get mixed up a little bit. So, like for example, like linearization, um, I know that they started researching it because of they wanted to evaluate square roots without a calculator back then. But now I don't know how they came to like this logic, and how they like came to this form, or why they even started researching such a thing. I'm sure it exists, but it's not within the textbook. The textbook just explains that many phenomena can be modeled with such models. So, anyways, that's besides the point. So let's take a function f of x, and if we differentiate f of x with respect to, I guess, x, or actually, you know what? Let's say t, because our book uses t, because it's time, and time is typically the variable that many functions will be in. So I guess we'll say that the df of t is going to be equal to dt equals k f of t. In fact, let's just say that this is equal to y to simplify things a little bit more, and equals k y prime, or I guess I could say dy dt. Oh, and not dy dt. I guess f of t would be, because it's the position, or the integral of dy dt. So anyways, or actually let's say ky, which will make things a little bit simpler for us. So let's take a look at this form on the right side here, and we see that k is, I guess we could say, a proportionality constant, but we'll get to a little bit of the logic later. And y is just the original function. So what function's rate of change is equal to a constant multiplied by its output? And there's many functions you can look at, but that would mean that there involves, and this is how I figured it out, this involves a chain rule of some sort, because the derivative function of any function is going to be itself, and then you just multiply it by the rate of change. So I know it's a form of, there's a function here. I guess f of kx is kind of the logic here, because when you differentiate this thing, the k comes out as a product, right? So that's the logic behind that. And you take a look, and for me, I figured it out because the name of the lesson was exponential functions. So I realized that, sure, it must have something to do with exponentials. And then you come to e to the x, which again is its own derivative over and over, which is a really cool thing, because that means the position is equal to the velocity, which is equal to the acceleration, so on and so forth, in terms of physics. So you can go on infinitely. That means it's equal to the jerk, then it's equal to the derivative of jerk, and so on and so forth. So that's pretty interesting there. Um, so that means that the function has to be f of x is equal to, let's say, or actually let's say y, or I guess f of t. F of t is going to be equal to Euler's times kt, such that when you differentiate it, you get f prime t is equal to k times ekt. So yeah, that's the logic here. But note that k is some arbitrary constant, which also means that this form works um, if there's a constant behind the e to the power of kt, such that this entire form works and k gets included in that c term here. But note that we can rearrange the function out such that k is on the outside. So k is equal to ky, and this is just the original function here back at this point. In other words, the only function that fulfills the only function that whose output times the only function whose derivative is equal to itself times a proportionality constant is the form c to the e to the kt. And that's really interesting because we get into further application of that too. But really, like, it makes me wonder, how did they come up with that? So, must have been some really smart people discovering this out. So yeah, that's the logic behind that. So let's get a little bit more deeper here. And what we're going to do is we're going to say that, again, we're going to model population growth with this because population growth is exponential. So dp to the dp, the derivative of population with respect to time is going to be equal to kp. So that means the population of at any point is equal to dp is equal to its derivative divided by its population. Or sorry, it's divided by the constant, which means that you can find the population with just its derivative and your constant, which is pretty interesting here, right? So we can also rewrite this as k is equal to the derivative times its population. And the interesting thing here is that let's say that this was constant here. That would mean k would be changing because as p grows, then k would also become smaller. So that means we know that these things increase. These things increase such that this is equal to a constant, which is really interesting, and that constant would be k in this case. And k is equal to the exponent in the form c e to the power of kt. So we'll get into a little bit of expansion here later. But we know that the constant, or this power right here, can just be evaluated by finding the derivative of this function. So f prime of x, or f prime of t, I guess, divided by its output, so f of t. So that's a pretty easy form to remember, just in case you ever do get lost. But this is just like pretty beautiful. Like, I love seeing how everything is coming together. And yeah. So before we get to some logic here, although we are using logic here, we have to use some, I guess, mathematical insight to understand what this actually means. And this basically means, like, let's say the population is changing at 2 people per second or whatever. This is the relative rate of growth. And how do we know this? Because dp over dt will give us how many. It's dimensional analysis, where dp over dt will give us how many people per time. And p is the population at that time. So it would be 1 divided by people. Or I guess population divided by people. Because this is the population, or this is the people. So if we cross this out, we get the, or I guess it was 1. We get how much of that relative percentage is changing over time, because you're dividing by a ratio, which is a little bit difficult to understand. But in other words, we're seeing how many populations are changing at that point, or how many groups of population are changing, which would probably be the better understanding of that. So in other words, k is equal to, in this population exchange, k is equal to the percent population changing over time. Population over time, which I'll just say over an interval of time, which is over dt. Because again, dp over dt gives us the population, or the rate of change at a population of a time. So it's dimensional analysis. We're dividing by p. The same way if you would do like let's say we have two cakes, and we divide the cakes um, by like a box. Then we're changing the cakes into the number of boxes, which is just further extrapolation. Again, it's just fractions. dp over dt will give us how much people we are gaining at that infinitesimal point of time. So just the derivative of people at that time. And this is finding how much people we have at this time, or the reciprocal of that, which means that the peoples cancel out, giving us the form of how many groups of people at this time are we changing per time, which is just a population. So again, it's a little bit difficult and abstract to explain with words. So again, I'll use a drawing to illustrate what's going on over here. So we're going to say that P of t is going to be equal to 4. Actually, we'll say P of 2 is equal to 4. Actually, we won't use numbers yet, but we'll just say P of t is equal to 4. So that means that at the moment t, there is 4 people. And let's say that the derivative of at t is going to be equal to it is going to be equal to 1, which means that you're gaining one new person every time. So you're gaining one person, but you already have 4 people. That means if you do the fraction, which is just P of t divided by P of t, which is just going to 1 over 4, you're only gaining 25%. I guess 125. No, it's 25%. Yeah. Well, because I said you're gaining. But you're gaining 25% of your original population. So in other words, the form before that we're given, which is dp over dt times 1 over p, is called a relative growth because we're comparing it in terms of percentages here. So again, that was just a fraction representation there. So yeah, that's pretty smart, pretty genius. So the relative growth rate will always be constant, which means that dp over dt and 1 over p will always cancel out to give a constant, which is pretty interesting. It's kind of like, well, I wouldn't say Boyle's law, but it's kind of like, I don't know, k is always constant, in other words. So that means p and dp over dt are growing linearly, or they're growing at the same rate, which is interesting, or they're growing proportional to each other. Or I guess that the same rate works too. Because that goes back to the original definition, which is dy over dt equals kt, or ky, which means that y is changing at a rate of itself times k, which is just beautiful. So someone who figured that out must have been quite genius, but I don't know why they were like figuring this out again, which is a little bit abstract to understand. So that's what a relative growth rate is. So let's give an example, and let's say that the rate of change, or let's say that 0.02 is equal to p. Remember that k, which is in the form c over kt, is equal to this number out front. So that means that we can automatically put 0.0t. And then we could solve for, or we don't solve for anything, but that means the form is equal to p equals po times e to the 0.02t, because remember po is just equal to c out front here, because at time 0 this all just becomes 1, leaving the c behind. So this can be the same as c, or this can be the same as p of 0, but it's the exact same form. You can just say p is equal to c times e to the 0.0t, which is this up front. To understand again why this thing is k up here, it's just chain rule, because the derivative of any function, and we'll use p of o this time, of this function, you can just pull the po out, ekt doesn't change, and then you chain rule times k. So again, k just comes over here, and p is just this entire thing, so we can rewrite this form as kp, and that's why k is equal to 0.02 here, to use some logic here. So now we have an example, and we'll go over a few of these examples just to help you get the logic pat. So we'll start at t equals 0, which is, or actually we're not going to denote times here. My teacher denoted the times, just so you understand. Let's say in 1950 there's 560 people, and let's say that in 1960 there's 3040 people. Note that obviously populations grow logistically, I believe. unless you have infinite resources. So this will not be an accurate model. um, Generally, it won't be an accurate model past a certain point, but population growth again is exponential. It's just that obviously you're gonna run out of resources or such, or other factors like illness or disease might break this model. So note that this is an ideal calculation, so it's not always gonna hold. So again, you could truncate this at 0 and you can truncate this at 10, such that p of 0 is equal to 2560 and p of 10 is equal to 3040. So this is going to be in the form p of t because this is the time and this will be the population at a certain time. The inverse function will give you the time at a certain population. So, so yeah, that's the logic here. So let's use some logic to understand. P of 0 in the form KCEKT is just going to cancel this entire thing out, giving us KC is equal to 2560. But we're given that P of 10 is equal to 3040, which indicates that we can use 3040 is equal to this entire thing out front here, 2560 times e to the kt, which again we don't know what k is, but we do know what the t is here. So now we can just solve for k using algebra. Divide 2560 on both sides. Get rid of the e by natural logging or ln or log base e, and divide by 10. And the answer should be 1.7185%, or the algebraic answer would be 0.017185. I think you could just times it by 100 to get the percent growth. So yeah, that's the logic there. Radioactive decay can be modeled the same way, except it's decay. So it's important to note that decay models also work. So relative decay is equal to negative 1 over m times dm over dt. So that means k of m, where k is the same constant, is equal to negative dm over dt, because we just times m on both sides. So again, you can use some logic here. But instead, here's what we're going to do. We're going to figure out what the half-life is. And this one's going to be quite genius or quite intuitive. We know that m0 1/2 is going to be equal to the half-life. So that means that the km 1/2 is just going to be equal to km over 2. So what is the derivative at km over 2? But to do so, we're not going to use this equation here. We're going to model it with m of t, which is just going to be m0 e to the negative kt, because again, km is equal to negative dm over dt, and using some logic, you can extrapolate this equation out of that. So if we can just set this side equal to m0 over 2, or the initial over 2 equals to mo e to the negative kt, divide m0 on both sides, natural log of 1/2, divided by negative k, it will give you the time or the half-life equation, which is pretty smart here. So yeah, that's the half-life equation essentially. So yeah, but you can also solve it backwards as well, solving for t. So, or we did solve for t, or solving for k, I mean, essentially. So now we know that so now we know about radioactive decay. Now we're going to go to Newton's law of cooling, which is pretty smart as well. So what does Newton's law of cooling state? And Newton's law of cooling states that the derivative of the temperature with respect to time is going to be equal to, again, the proportionality constant, which is, or just k, times the temperature minus the temperature of the surroundings, or the temperature of the surrounding medium. So for like example, if you left a hot coffee in a room, it would be equal to the temperature of the hot cup of coffee minus the temperature of the room times that proportionality constant. So in English, you would say the rate of cooling is proportional to the difference of the temperature to the surrounding temperature. So also make sure it's ambient temperature, and make sure that temperature is pretty constant. Otherwise, it gets pretty complicated here. So we're going to set the function y is equal to t minus ts. So that means dy or dy over dt is just equal to dt over dt minus ts, and again we're assuming it's ambient, it's constant, so that cancels out. So I guess we don't even have to put that subtraction sign there. Um, so yeah, there's that. So which means that the rate of change is just going to be equal to k times the difference in surrounding temperature, which is how they came up with the equation. Or not how they came up with the equation, but how we can get it to that form. So let's do an example question, and let's say that y of 0 is going to be equal to, or that y is equal to the difference in temperature again. And that's just going to be TO minus 44, indicating that the surrounding medium, or the room, is at 44 degrees. And Y30, or that at Y30, or Y30 minutes, it's going to be equal to 61 degrees, which the difference is 17. So again, we just apply the same formulas here. 17 is going to be equal to the initial temperature, which is, well, not the initial temperature. We solve for the initial temperature because y of 0 is going to be equal to TO minus 44. But we're given that the initial temperature is at 72, which gives us the initial value at 28. So it's going to be equal to 28e times k to the 30, and then you just solve for k. And solving for k is pretty easy. It's just going to be 17 divided by 28. Natural log on both sides divided by 30. So just divided by 20, which crosses that out. So I just did the algebra there essentially, and you get the k, which is equal to negative 0.1603. And then we get the form equal to t of t is equal to 44 plus 28 e to the negative 0.1603 t. So pretty ingenious stuff here. We found the k and we modeled it using the exponential function again, which was pretty smart. And yeah, that's how you model temperature. So yeah, that's pretty smart. That's how they figured it out. Or that's not how they figured it out. I'm not too sure how that equation was figured out, but that's the answer to this question. Also, something interesting to note here is finance, which is pretty smart as well. So Leonhard Euler, who comes in like the, I think it was the 1700s, he discovers the constant e, which is essentially the limit as x approaches infinity of 1 plus r over n times rt. Or I guess it would be the rate divided by the amount of compounding times divided by the amount of compounding periods times rt. And that is equal to e, which is approximately equal to 2.71828. But my question is, did he figure this out? I mean, I'm not so sure. I didn't do the research. But like I don't think they had this modern finance back then. So I don't know like where this thing originated from, but it's super important to use. I think it is super important. It's irrational and it's transcendental. So yeah, it's pretty important. So this is the compounding formula, which states that if we have like 5% interest, let's say, and let's say we compound it quarterly, which is 4 times per year. So I'll just say 4/year. And that means that we get 1 plus 0.05 divided by 4 times 4t. And we do this infinitely. As x approaches infinity, we get the form 1 plus 0.05 is equal to 99999, and using exponent rules, we could just pull the t out. That's just going to be equal to e to the power of t. So again, it's modeled exponentially. Finance is modeled exponentially, and the formula you'll use is a equals p0 ERT, or I guess a0 in this case. P will be population growth, so a0 ERT. But a lot of people say a equals PERT, which is how I kind of memorized it back in a while ago, which is just the principal times the the principal amount, which would be the initial amount, times the the function essentially, or that is the function, but principal times the exponential growth function. So yeah, that's all about 3.4.